Hey everyone, so in this video we want to talk a bit more about collision behavior. So how do our points react to a collision? We already talked about this, but I want to go deeper into this. More specifically, we want to talk about sticking and sliding. So what we have here as a setup is similar to what we've already seen. We have a sphere here that we emit from. I already gave my points a p-scale attribute and a red color. And then what comes out of my simulation are points, only the points, not the collision objects. The geometry here, of course, comes in as a static object. And then I copy some spheres with a radius of exactly 1 onto those. And when I look at it together, I can simply see my points better because they have a p-scale. And the default behavior is this. They just bounce off because those are the default physical settings. So none of this should be surprising to you. Pretty basic stuff. Now, we already talked about that you could think that if you now change the friction to something very high, that these points will stick to it. But as we've seen, let's quickly do this. Let's go extreme. We turn off all the bounces, including the bounce forward, keep the friction at 1. But for the static object, we do the same, but this time we set the friction to 100, just to be absolutely sure that this is a very high number. And as you can see, we do not get any kind of stickiness. So this is not how stickiness works. Instead, what I showed you is that in the pop solver, we have under collision behavior the option of a response. And now here there are multiple things we can do, and let's quickly go through them one by one. By the way, I pinned my view here so that we can see the whole thing from outside as spheres. If you go into the .NET, it would of course only show the points usually. So when I set this to die, what will happen is whenever points collide with something, they will not disappear as it may look like, they just die, they will be deleted. So this can sometimes be helpful. For example, if we wanted to emit new points from the point of collision, this is something we will look at in a later video. And then we have something that is similar to the stick that we already saw, the stop function. So what this means is as soon as an object finds a collision, it just stops in space. This can be interesting when my object is not moving. If my object would be moving, then what we will see is that the points would stay in space. So let's quickly do this by adding a transform here that moves my box up and down with a sine wave. And now, unsurprisingly, when we look at the result, you can see the first of all, inside of the PopNet, the movement is not recognized yet, as you can see, because in the static object, we have to make sure we activate use deforming geometry. Now it should work. And what we will see is that the points stop, but they stop in space wherever there was a collision. So this is not what you would expect. So this is the difference to when we set this to stick. It will literally stick to the object even when it's moving, which is really helpful if this is what you're after. So that's the first option. For now, let's turn off the animation again. By the way, even though it's very obvious now which points are sticking right now, we can actually also visualize that for ourselves if we go into the PopNet, and let's make sure we unpin our viewport so that we can see it from the inside. And you can see that my points are currently all red anyway, because this is what the color I gave them. But if I would quickly turn this off, because there was a bad choice of mine for showing this, and now they're black, you can actually, in the pop solver, make sure that you visualize this response with a color. And this is here the color hits. So when I activate this, it will show me everything that is currently sticking. And here you can see that it will turn all the points red that are currently sticking to our surface. In more complicated cases than this can be really helpful to make sure that the sticking is actually happening. But this is just a side note, so let's turn this off again and let's make sure that we see our spheres as red again. So that's the first thing. That is why stick is better than stop in certain cases. And now let's talk about by turning off the animation again, and let's turn on the slide function. And what this means is that the points, like the name suggests, will slide on the surface. Now that does not mean that the points will not be able to leave the surface of our object, but they will basically try to slide as long as they can. We will talk about this more a bit later in this video, but what you can use this for example, is droplets or something that move along a surface. We will look at different ways of doing this in a later video, but for now this would be one way of letting, water, for example, flow along a surface. So these two things you can set in the PopNet under collision behavior, or these four actually: die, stop, stick, and slide. Before we go deeper into this and looking at an example what we can do with this, first of all, just for you to know, when an object is sliding or sticking, it actually gets an attribute that you can read out to find those points. So for sliding, which we have here, unsurprisingly, the attribute is actually called sliding. And it is an integer. So when we middle click at the PopNet, we will find the sliding. If we look for it, there it is, sliding. And to find which points are sliding, we could do the following. Because this attribute will stay intact through the copy to points, we could say, okay, turn everything green for the points. And it's important that to change the group type, otherwise the expression will not work. And show me everything where sliding is 1. And here you can see it happens for the points that are colliding with the object. Now what is a bit weird here is that only the first couple of points turn green here, and that is because those points here actually are not sliding on the surface anymore. It might look like it, but they actually already are disconnected. We will see later on there is an attribute called cling that controls how long a point will stick to the surface, or basically how magnetic our surface is. But generally the sliding attribute will show you all the points that are currently sliding on the surface. So this is actually not wrong. This is actually what's happening here. We'll look at this later on. Where it's a bit easier to understand is the stuck attribute, which unsurprising happens when we switch this back to stick. So it's not sticking, unfortunately, because that would make too much sense. The attribute that we need here is called stuck. And whenever this is 1, we know that this is a point that is actually sticking onto something. And here you can see this makes a bit more sense. Everything stays green as long as it's stuck. And of course, as we've seen, that also works with moving geometry and then looks like this. So this is kind of helpful for a simple case like that. But in production, it actually is a bit more complicated. And for this, let's look at an example, what you could potentially do with this. And that is, if we have some wheels and we want them to drive through some kind of snow that we represent in form of points. And by the way, this is something we will talk about later. I can make the points visible as spheres with this visualize node. We will talk about this in the grain chapter, so just bear with me for now. Instead of doing this, you could just copy spheres onto it, would work just as fine. This is just a little bit faster. First of all, what I did here is I have just a couple of points scattered on a grid, nothing special. And then with an attribute randomize, I set the p-scale to a random number so that when I then look at the result, we have different sized spheres. And then I scatter just a lot of them. And then the wheels here are just animated so that they move through that snow. Now, if I stick that in with the setup we usually have with a pop object that defines here our start state, because I don't want constantly new snow to emit, I take the first input of my snow points here as initial geometry in my pop object. And then I, let's say, have a gravity on and my static object, which is my wheel. And because it's moving, it needs a deforming geometry. In this case, by the way, I use the surface collision because it makes a bit more sense for the precision problem here. Now, what happens is not necessarily what you would expect. First of all, of course, the snow will fall down because I haven't yet clicked in the ground plane, because I want you to be aware that the ground plane now creates one problem. First of all, I mean, it works. But we don't have yet the sticking function. By the way, unfortunately, as you know, the Houdini viewport is not very good. So don't be too confused by this shadow here. This is simply not a very good shadow calculation. You can see there's always a bit of a bright effect right underneath the wheels, which is unfortunate because it simply gives you the impression that the wheels are floating, but they're not, as you can see here. This is what this transform here is for. And when we run this now, you can see that there will be, and actually let's make sure that we only take the particles out of our simulation and not the ground. It's then easier to see the whole thing. And what you can see is that our wheels currently push our points apart and move them a little bit, but there's nothing sticking here. But what we want though is we want our snow to stick on the wheel. And for this to work, as we've learned, we can go into the pop solver and set it to stick. And now you would expect that the snow will stick to the wheel just like it stick to the box before. Unfortunately, as you can see, it doesn't work. So why is that? To figure out what actually is going on here, as we've seen, we can use the color hit function to visualize all the points that are sticking to give us a hint what is actually happening. And as soon as we turn this on, this now actually becomes more useful than in the last example. It shows us the problem. We are actually colliding with the ground. And this means that all the points are currently sticking to the ground and not to the wheel. So this is a very common problem. Even if you have multiple objects, this can happen, because very often you want, like here, a different behavior based on the object. Now, first of all, you might assume that you could use here the group to effect or even the collide group. But this unfortunately is not working because the group to effect means the point. So what you could do is that you say certain points can be sticky and others can't. But this is not the problem we have here. And the collide group is another thing that we could use, but it's a bit more complicated to set up. So let me show you something else. Because when you want to have different reactions or responses to a collision based on the object, I would recommend not using this collision behavior in the pop solver. So let's turn this back to unchanged and let's turn off the color hits. But we can actually create multiple collision responses based on the objects. And for this we can use the pop collision detect node. Now really quickly, when you type in pop collision, you find two other nodes. Pop collision ignore can do the opposite. So you could actually use that to make sure that certain objects should not be considered for a collision. I will skip this for now because that's very rare that you need that, but look into this if this interests you. And the other thing is pop collision behavior. And I just want to quickly show you this pop collision behavior is similar to what we saw in the pop solver. We have color hits, we have response. So this looks like what we need, but this is just inside of the pop collision detect already. So when we select the pop collision detect, under behavior, you can see the same things. So you don't need the pop collision behavior because it's already inside of the pop collision detect, but the pop collision detect gives us a lot more options. So don't be confused. The pop collision behavior and pop collision detect are basically the same thing. The pop collision detect is just the nicer version of it with more functions. So in my experience, what you should connect this to is the first input, the pre-solve of our pop solver. So this should be calculated in the beginning of our simulation, not at the end of the frame. And what you can do now here is you can set certain behavior specifically for certain objects. You can find this under collision, because here you can set a certain object that the collision should happen to. If you don't set this, let's quickly try this. We set this to stick again and the color hits of red. You can see that it just happens to everything just like before. But now if we wanted to have our points only stick to the wheel, all we have to do is we change under collision our collision target. And there are multiple ways of doing this. You could use just the context geometry, so wherever our wheel comes in, which in our case is the fourth input, here it is, you could just change this here to the fourth context geometry, and then it will understand, please only do this collision with the object that comes in the fourth input, therefore our wheel, and then you can see this already works. And it turns red because we have our collision hits turned on. Another way of doing this, depending how your setup is, you could use dop objects, because this wheel is inside of our simulation, and let's make this a bit higher than my head, represented in form of our static object here. So we have our ground plane, we have the pop object, and we have the static object. So all we have to do is we type in static object 1. And a small hint here, you don't have to write this out. If you only have one static object, you can just do this. Static star is totally enough because it will now find the static object under that name. And now if you run this, you can see it also works. So multiple ways of kind of finding our wheel here. And the last version actually is to just use an absolute sub path. So if we wanted, we could even do something like this. We create a null out here and call this out wheel, for example. And I copy this. And then we could even use that as an absolute path. So many ways of finding your collision object. Feel free to choose whatever works for you. And now you can see our snow is sticking to the wheel. And when we look at this from the outside, it even looks quite cool because I gave our spheres again a little bit of a p-scale. And now you can see we can stick our points to an object and only to that object. So this is pretty cool. By the way, keep in mind when you use surface collision for this, as I did for the wheel, here surface collision, we talked about this in the collision video, then the p-scale of our spheres will be recognized. So that means depending on where our wheel is, we could even make sure that only the big spheres are hit and not the smaller ones. And this is why I originally didn't have this transform here. So when I let my wheels float a little bit, before it was like this and now it is like this, then only a few points can be grabbed. And this can look just a bit more natural when a couple of points are left behind. And that didn't work. So let's try this again by maybe doing the opposite, by moving it up a little bit. Yeah, okay, this is a bit, well, it's not too bad. Let's keep it at that. So as you can see, the effect is that not all points will be taken because of course it depends on the distance to those points. Just as a side note, stuff like that can make your simulation much more believable if it's not absolutely perfect. Oh, by the way, I just realized there's something that we had on the whole time. I'm sorry I didn't see that. Our points are bouncing back and forth, and this is because on the ground there's still a bounce happening. So let's quickly fix that by turning the bounciness of our points off. Sorry about that. Now we will come back to this example at the end, because I want to give you a little idea what you can do with this on top. But before we do this, let's actually talk about sliding a bit more. And the wheel example is not a good example for this. And the example we want to look at here is quite simple, because it's then easier to see what's going on. I just have this here as my source. I turn it red. I give it a p-scale so that I can visualize my points later as spheres. And then I use the sphere here as a collision object in form of a static object, nothing special. And then I use this visualize node again, where I set the points as sphere so that we can see them better. Again, this is something we'll talk about later. It just makes them easier to see. And then you can see that they just collide with the sphere with a little bit of a bounce, which you can see a little bit that some of them bounce off. So this is a normal behavior, and we want to make sure that they slide around the surface. So again, imagine them as drops or something. And it's easy to do. We just go into the response of the collision behavior and set it to a slide. Again, we could also use a pop collision detect to control this on a per object basis. And when we now look at the behavior, we can see that nothing bounces off anymore, but they actually slide on the surface. The reason I wanted to show you this example is that maybe this is not what we want though, because if you would imagine this as droplets, you might expect them to slide around the surface until they hit the bottom part. And this is where it's a bit limited to just turn on slide. And maybe you would think you could find some kind of stickiness or something, some kind of attribute that you control this behavior with, but unfortunately it's not here. And this is where an additional attribute comes in specifically for the sliding function, and that is cling. And cling is a float, and this describes how long basically a point is sliding, or how magnetic, let's call it, the surface of the object is. You can actually just set this yourself, as we've seen before with a pop wrangle. It's just an attribute. You could even set it before the simulation. Actually, let's do this, because that's the common way that we've seen so far, and we can do the same here. So let's set the cling to a higher number than 1, because 1 is the default actually. So let's say we set this to 10, because then we should definitely see a result. And let's see what happens. And you can see that they don't kind of leave the surface as early. It takes longer for them, and this one was pretty good, before they actually fall off. Now let's go further with this. Let's set this to 30 maybe. And now you can see they only leave the surface pretty late, actually too late, because when we wait a little bit, you can see here that they basically roll around the bottom and can't leave it because they're not fast enough. Now I cannot fully explain to you what this number here exactly means, if it's velocity or what it is, but the best way of dealing with this is just change the number until you have something that works. And of course, if you would scatter your points as a source yourself, then you could actually even give every single point a different cling number. But here you can see with a 20, this works quite okay. So let's now quickly, just for the sake of it, show you that this is a good idea to set this on the source, but you could also do it inside of your simulation with either a pop wrangle. So let's set again the cling to, let's say 30, a bit too high as we've seen, but to make sure that actually happens. And there you can see, okay, it's too high, so this worked. Or as we briefly showed in the physical properties video, there's also a node that I personally find unnecessary, but why not mention it, the pop property node. So here you have all kinds of attributes that the simulation understands, and under dynamics you have also here the cling. So if you like that more, you can also just set it here. But again, all this node does is, as usual, setting an attribute, so you don't need this node to set pop properties. And here now we set it to 20, and as you can see, we have the behavior that we saw before. And again, our little rogue point at the end. So this is now the cling attribute that I wanted to show you in combination with a slide. Pretty important because you need it to control the behavior of your sliding. And quickly coming back to our example from before, where we looked at the sliding attribute, let's quickly adjust the cling attribute here as well. This time with the pop properties, you will find the cling attribute under dynamics, and let's set it to a high number like 30, I don't know. And then when we rewind and look at the result, you can now see that our points, unlike before, are now actually sliding the whole time until they can't slide anymore and leave the surface. Now we could finish here because those are the most important things I wanted to show you about this, so that we can control the stickiness, read out when something is sticky, we can visualize it, we can make sure that we set the stickiness and the sliding behavior for different objects, and we've seen that we can use the cling attribute to control the sliding behavior. Because I showed you this example though with the sticking on a wheel, I just wanted to kind of finish this, because what would be very common here for this example is that I want to have some snow fall off the wheel again. Just for you to understand, this is nothing we can do with the tools we've seen so far directly, because you might think, well, maybe this could be achieved by changing our behavior to slide. And then maybe, if we're really clever, we change the pop properties to a cling that might give us our result. I don't know, let's try 10. And this certainly will change the behavior, but not to what we would want. Because what now happens is that they slide on the surface, and because of the behavior, they kind of move down again. So they will never travel with the wheel. So a slide is not what we need here. We need actually still a stick. And because we need a stick, we can't use cling. So how would I solve this problem? So let's go back to stick. And because we moved our wheel a bit higher, this is currently what we get. Only the bigger spheres are sticking because only those get in contact with the wheel. And what you can do here is you can just use the attribute that we learned, which is stuck, and just not only read it out, actually it's an integer attribute, but you can override it. So let's use a pop wrangle again. And to be honest, there might be another way how to do this. Please feel free to let me know in the feedback or something. But the way I would do it is just changing the stuck attribute to 0, for example. Now, of course, if I would do this, then I would override it for all the points, and then I would not have any sticking anymore. That's pointless. But I could do something like, okay, there is a certain chance that my points will fall off. And this is something I explained in one of the first videos in the Vex chapter, probability. So I could say I generate a random number for each point. In this case, I don't use ID, by the way. I use ptnum because we don't emit those points. And when I compare this to point 1, there's now a 10% chance of every frame that a point will fall off. Now, if I would do this, this will not work, unfortunately, because it means that every point will have the same random number every frame. So in other words, yes, 10% of all the points will not stick, but they will never stick. Neither in the beginning nor during the simulation, they will never stick. So what instead we want to do is we want to make sure that this is different every frame, as we said, because every frame there should be a new chance that a point is losing its stickiness. So let's try this now, and now you can see this actually works much better. Some points will, be the 10% on every frame and fall off. Unfortunately, we have way too many. This is normal because 10% every frame, this is a very high number. So let's lower this to just 1%, and this will probably feel much better. Yeah, and here you can see some points just during the simulation fall off. Now, I admit this is a bit more advanced, but since I decided to show you this example, I should do it properly and actually also show you how I would work with these attributes. If you're not too familiar with Vex, I would highly recommend getting used to this. This is what you would have to do every day. So this is a good example where you would need a Vex solution, because frankly, I would not know how to do this without Vex. But either way, even without this Vex part, I hope you learned a little bit about how to deal with sticking objects and sliding points. So play around with this and maybe look into a bit more advanced versions where you change these attributes yourself. I hope this was helpful. Thanks very much and see you later. Cheers.